Hello YouTube. So now here I am. Okay, of course as such it is not such a big thing to create a YouTube channel, to upload videos on the channel, to produce the videos, or produce is maybe a too high word, to make the videos, to make the titles for the videos, to make the descriptions for the videos, or to make no descriptions for the videos, to make the thumbnails that are the pictures that are shown if a video is proposed, and to make the other pictures for the channel. But for one, small things are big things. Things which I in general consider to be small, things which I in general consider to be big. For one, big things are small things. And solving on a beer mat 100 years physics mystery. That is the title of this video. This is why this video is made, and this is what this video is about. And now how this video, how it is constructed. First I show it that where first I do a fast forward version of it, and thereafter I do a version in normal speed. Of course, the version in normal speed is also put in shape, but it is a normal speed. And while I write it down, I comment on it, on what I write down. And thereafter I say something about it, what I just made. I comment on it, I say something about it. And thereafter I still also have something. And the mystery, the name of the mystery here, that I don't reveal, that I don't say. Of course, if you go on my YouTube channel, I've already uploaded 2 videos there. I have uploaded 2 videos there. I've published 2 videos there. If you look at them, you easily find the mystery. But what you don't find so easily is how important this mystery is in physics. Because there are of course many 100 years physics mysteries. There are of course also many 100-minute physics mysteries, or 10 minutes physics mysteries, or 100 days physics mysteries. You know what I mean, or what 1,000 years physics mysteries. Where of course the older the mysteries are, the more likely it is of course that if the mystery is small, minor, not so important, that they are forgotten. But I could have digged out some nice, small, minor, unimportant mystery, unimportant, small, nice, minor, unimportant 100 years physics mystery. And now I have a nice topic to this video, and I can make really nice clickbait. But okay, let's start. I first draw a graph, a diagram, a figure. where on the y-axis of the diagram is the electrical resistivity ρ drawn, and on the x-axis of the diagram the temperature T is drawn. And in the diagram, the electrical resistivity decreases with decreasing temperature. But this is arbitrary. The electrical resistivity could also increase with decreasing temperature, or decrease and increase with decreasing temperature. This is arbitrary. And at a certain point, at a certain temperature, this certain temperature is called transition temperature or critical temperature. At a certain point, at a certain temperature, the electrical resistivity drops to 0 and stays then there at 0 below. But why? Why does the electrical resistivity, why is there no resistance anymore for these temperatures? Why? This is the absolute 0 point, where the electrical resistivity is absolute 0 and where the temperature is absolute 0 Kelvin. Where, of course, it is said a quantity, a value of a quantity is 0. If, of course, in an experiment, if something is observed, it can only be observed, it can only be measured with a certain measuring uncertainty, with a certain finite measuring uncertainty. But if this finite measuring uncertainty is so close to 0, if it can't be differentiated from 0, if it is so close to 0 that no difference to 0 can be observed, then it is said it is 0. This is the experiment and the theory. The formula, standard microscopic formula for the electrical resistivity is the Drude formula, which is in classical equation, but which can be also extended to quantum mechanics. And in the Drude formula, m is the mass of a charge carrier, An electron, the charge carrier, often it is. And the larger the mass of a charge carrier, the harder it is to accelerate to move the charge carrier, and the larger the resistivity. And E is the charge of a charge carrier. And the larger the charge of a charge carrier, the easier it is in an applied electric field, in an applied voltage, to move, to accelerate the charge carrier, and the smaller the resistivity. And N is the density of electrons, of charge carriers. And the more charge carriers there are in the material to be accelerated, to be moved, the more electric current can flow, and the smaller the resistivity. And tau is a scattering time, which is a time which describes how electron charge carriers are scattered in the material. If a voltage is applied, the electron charge carriers are accelerated, are moved through the material, and are scattered and slowed down on the material. And the smaller the scattering time is, the more often it is scattered, and the larger the resistivity. If the electrical resistivity is temperature dependent, as it is, one or more than one of the quantities in the Drude formula must be temperature dependent as well. M and E, the mass and the charge of a charge carrier of an electron. Of course, there are many model scenarios in solid-state physics, where it could be also that there are scenarios, models, in which these two quantities show temperature dependencies, but here they are not. They are constant values. N, the density of electrons, of charge carriers. This is a quantity which can vary very much with temperature. For example, in semiconductors, charge carriers electrons are bound to certain ions in the semiconductor, are bound to certain ions, but can be freed from their bounds by temperature, with increasing temperature. Then they are freed, and they can be moved, accelerated in the voltage, and contribute to the current. And for these temperatures, when they are freed, of course, then the density increases much and varies much with temperature, and the resistivity varies much with temperature. But in normal metals, in normal, not unnormal metals, the phenomenon on the left, the drop of resistivity and that it stays at zero, is also observed. And in normal, not unnormal metals, it is a solid understanding that the resistivity of these normal, not unnormal metals results solely from scattering. Its cause is solely scattering, and not the temperature dependency results not from a temperature dependencies of the density of the electrons. The density of the electrons is a constant value. The resistivity of normal, not normal metals results solely from scattering. And this is why the Drude formula, the temperature-dependent Drude formula, has the form it is shown here. And now the question that stands here, that is here, and that I now also begin to answer. And the essence of the answer is also shown with these two names. And the scattering time, the time within which electrons are scattered, reaches at a certain temperature, at a certain energy, since temperature is energy, Heisenberg's uncertainty relation. An electron has an energy because Boltzmann, the equipartition relation, temperature is energy. And the energy and the scattering time reach Heisenberg's uncertainty principle, energy its limit. And this is my suggestion, proposal for why. At these temperatures, the electron has an energy and a scattering time, which is under the border and limit by Heisenberg's uncertainty principle. And there something happens, and there something new happens, which has as a cause, as consequence, what is seen here, where I choose this limit to be to equal 2h bar. And these two equations, these two relations, Heisenberg and Boltzmann, can be inserted into each other. And this gives the equation that is here, that comes here. Now, for these two unknown quantities, T and tau, the temperature and the time. And the other equation for these two quantities, for these two unknown quantities, is above, is the temperature-dependent Drude formula. And these two equations can now be equated. These two equations for these two unknown quantities can now be equated, and the result at the bottom, which comes at the bottom right, is obtained. There is the result. And if two equations with two unknown quantities are equated, and if this has a solution, it can be solved, and it can be clearly solved. Where the equipartition relation. The equipartition relation is a classical equation, is a classically derived equation, where of course temperature is energy, is valid overall, but the states, the energies. The quantization of energy of an electron for typical millimeter-inch large samples is small. These quantizations of energies are small compared to the temperatures, the energies at which the electrical resistivity drops to zero and becomes zero. These temperatures here, where the electrical resistivity drops to zero and becomes zero, is large compared to the energy difference of the nearest neighbor states of the electron. It is large compared to the quantization of the electron. Compared to this, the energy quantum is small. The energy quantization of an electron is small. And if the electron quantization is small, if the energy difference, the minimum amount of energy between nearest neighbor state, if this is small, then the energy of an electron appears to be continuous. And if the energy of an electron appears to be continuous, it is classical. And if it is classical, it can be treated classically. And if it can be treated classically, equations can be derived classically. of course, to evaluate now, or put a line through the of course, strike the of course through now, to evaluate. What do you think of it? What do you think of it? And I don't expect anyone to watch this. By what do you think of it, I mean, of course, you're free to react to it, to comment on it, to react. But what I mean is really, what do you think of it? Okay, now I don't know what to say, so I say what is in my head, what goes through my head, what is in my head. On the one hand, if you're not interested in physics, that sounds negative, I know, but I did not come up with a better word. But if you're not interested in physics, you're not interested in physics. Okay. And on the other hand, or I prefer to say on the third hand, if you are interested in physics, if your profession is in physics, if you have spent much time in your life with physics, if you're in physics, into physics, in with physics, then there is what I have written down, and the three formulas equations. They are of course known, well known. Well, the Drude formula is known. It is not such well known, but it is a known basic fundamental formula. But the other two formulas equations, the Boltzmann equation, the equipartition relation, and the Heisenberg relation, Heisenberg's uncertainty principle, they are well known. But every equation formula in physics has its limits, is derived under certain circumstances, holds for certain conditions, and is also the quantities in it. You can put a formula equation on paper or on your computer, but the quantities in it is still another thing, how they can be applied, which the quantities in it, the physical quantities in it may be easy, look easy, but if you have a concrete problem, a concrete material, and you try to find values for these quantities, to find them, that's already different and more difficult. And this is why, even if you are interested in physics, now just seeing this video, just seeing that what I've written down and the three formulas equations, known and well known, you still should be familiar with them. You should really well know all of them. And this is because in physics there are so many formulas, equations, so even if you are interested in physics, it's still... And this is why if you are not interested in physics, and if you are interested in physics, you maybe, for that, you are not so far away, and maybe there I come back to the other hand, maybe you both are not so far away from each other and both are not so far away from the other hand. Questions. There are questions now, of course. There's the question, what is behind all this? What is behind me, my person? What is my history in physics? What is my relation to physics? What is my position in physics? Where am I in physics? And what is behind the writing? What I have written down, what I have derived, what I have inserted into, what I have put into. Unit-wise, it is okay, everything comes out right. But the how, the picture, what I here have is new. The physics is new, and everything that comes with something new comes here also with. But I have thoughts why. And there's the question, why do I do it here on YouTube, on the social media platform? If YouTube is a social media platform, I think it is. Why do I publish it here? Because I also publish it here. I also did it publish somewhere else, but I also publish it here. And because the typical regular way to publish scientific research is this not. The typical regular way to publish scientific research is to publish it on a scientific journal. So why I did it here also. These questions, but I don't answer. And there's the question, theory and experiment. Theory and experiment, what physics is. Theory and experiment physics. What I have written down, what I have derived at the bottom. I derived this mathematical expression. This mathematical expression which has physical constants in it, but also has simple quantities in it. But as already mentioned, even if the quantities are simple and one takes simple materials, it is not that easy and straightforward to just put them in and then to easy find it out. To get good established quantities, values, it is not so easy, but some can surely be done to see how does it fit, how does my theory, how does my result, how does this my mathematical expression fit the experiment. And this, the answer here to that, I don't answer. So now 3 questions. These questions I say now here, one after the other, but I don't answer. So why? Yeah, it is, yeah. I can say to that, life is not always proportional. Life does not always go proportionally. It is not always the more you put in, the more you get out. This is of course subjectively, but it is also objectively. Objectively, one knows how much one puts in, and one knows how much one gets out. And life does not always go in a line. It does not always go linearly. It is not a linear life. Okay, that to that. The fast forward version, the commented normal speed version. I said something, I said to it, I comment on it, and I said something, and now still the something. And this is now off the topic. This has nothing to do with it, but I still say it. When I did prepare for this video, I did dived into how video cameras work and what video cameras that do. This is really, they do something 30 times a second. I adjusted it, in my case, to do it 30 times a second. And it does this for a 60th of a second. It switches an image sensor on, that it becomes sensitive to light and the picture can be taken. But there are also video cameras or cameras with small mechanical shutters that opens up for a 60th of a second or much shorter times. This is really what everything is possible. And also how from these pictures, movies, videos are made. The pictures are shown one after the other. And if they are shown fast enough with a high enough frequency, then it appears to the eye as a video, as a movie. But how even big studio, movie, cinema, production companies, how they produce movies, how many pictures they take a second, and how this has changed over the history of making movies, how this has changed, how many pictures they are shown in a second, and also how each of these single picture look like. This is really, but okay, that was to that, and now to the smooth end to this video, to the smooth end. Okay, now the smooth something end to this video. I still have something. This is it now. The beer mat. The beer mat is the object of this video, and with the mat there is the beer is connected with it, the beer. And I take here a wheat beer. And what I will do now is the following. Here in Germany, I'm in Germany, it is something, if wheat beers are served, it is something, it is a skill. If they are served, then the wheat beers are poured into wheat beer glasses. And the wheat beer glasses are specially made for the wheat beer, and it is the skill to pour the wheat beer in that it looks nicely in the glass if it's fully poured in. And what this means is there, if it pours in, there gives a foam, and this foam should be nicely on top of it if it is poured in. And that I now do, and we'll see how it will be. And for the wheat beer, I choose the one and only Butler Physics non-alcoholic wheat beer. So, and why do I choose it? Why do I take this beer? Because of the taste. When I'm done with the video, what this means, if it is done, if the timeline is at the end, the beer is poured in, finished, and the end of the video done, then I will drink the beer. And that's why I take the taste. And now to describe the taste. I'm not a native English speaker. So, and I searched my internal dictionary in my head for a word to describe the taste of it. But I didn't find one. So then I searched, of course, the next step is to search with an external dictionary. You can probably think which dictionary I used to find a word for it. And I found one. And this word is the taste of the Butler Physics non-alcoholic wheat beer the taste is high brow. And I now show it also because it's also a new word for me. I try something. Yeah, that's the word, highbrow. And that fits, that is its taste of the beer. And that's why I took it and why I chose it. One can say it's the sweet beer is a true highbrow wheat beer. And because it sounds so good, I say it again. It's a true highbrow wheat beer. And it is alcohol free. It is non-alcoholic. Okay, and now I do some preparations and then I'll do it. and goodbye. Because when the beer is poured in, I put it on the table and then it is done. So this is why goodbye. And thank you for watching. Thank you. And one thing just as information, as a background information, I haven't done this pouring in wheat beer in a wheat beer glass for a long time. As said, I'm in Germany, my feet are on German ground, so what does it mean? Here it could mean that in Germany this could mean I haven't done this like for 72 hours maybe, but in my case, I have done this, the pouring in the wheat beer glass the last time a half year ago, and then I also didn't do it intentionally. The last time I did it intentionally was 1, 2, 3 years or more, something like that ago. But now, let's do it. Okay, now the preparations were made. There weren't much preparations. The biggest was maybe here, putting up my sleeves. So, and now to my skill of pouring in wheat beers. Where of course first the mat, because that what a mat is for, that what it is made for, that what it's used for, and that is what it's concepted for, and what it is specified for, and what it is tested of. This is what a mat is made for, and nothing else, nothing else. And if you use it for something else, but okay, then and you there, don't look so serious. This is just de-serious. If this is de-serious, this is nothing too serious. So just, yeah. Yeah, that's a better look and more, yeah. Okay, now I start.